So, hi everyone. My name is Jose. I'm a core and platforms technology analyst working on the innovation and standardization activities within Telefonica Group. In this session, I'm going to provide an overview of the ongoing POC at ETSI ZSM entitled Automated Network Slice Scaling in Multi-Site Environments. This POC leverages OSM auto-scaling capabilities to provide upper service orchestration layer with necessary means to modify the resource capacity of a slice in an agile manner in response to unexpected load surges. Although most of innovations are developed at the service orchestration layer based on OpenSlice solution, in this presentation, we will focus on the work on the OSM layer. So, in this slide, you can see at a glance what the POC is about. Roughly speaking, this POC aims to demonstrate the capability to automatically scale out a network slice instance that is deployed across multiple administrative domains. The POC has a 3-month duration ending on the 31st of March. This means that we are at the final stage, just 3 weeks away from POC project end. And for the execution of this POC, we leverage the 5G assets of 5G VINI, which is a large-scale end-to-end 5G facility composed of distributed European Union nodes, each deployed at a different geographic location and defining a single administrative domain. One example of this node is 5Tronic, and the management and orchestration of the individual 5G VINI facility sites and the enablers allowing for their interworking are aligned with ZSM architectural design principles, use cases, and network slicing views. Here you can see the POC team formed of 2 CSPs, namely Telefonica and Telenor, 2 universities acting as BNF providers, University of Patras and University Carlos III de Madrid, and 1 open source community called OpenSlice. Now I will provide some background information on 5G VINI, the role of OSM into our POC, and what is OpenSlice. So first of all, as said at the beginning of the presentation, this POC will be executed using the 5G assets of 5G VINI project. 5G VINI project has the mission of build an open, large-scale 5G end-to-end facility, providing advanced 5G VINI capabilities that are made available to industry verticals for use case trialing. This facility provides every vertical with an isolated service experimentation platform deployed in the form of a slice. This means that each vertical will use the provided slice to set up 1 or more use cases, validating their KPIs under different load conditions through the execution of different test campaigns. As illustrated here in this figure, you can see the 5G VINI facility. You will see that it's a pan-European interworking facility formed of different sites, each corresponding to a different European Union node and defining, as I said before, a single administrative domain. In total, there are 4 main facility sites. You have Norway, UK, Spain, and Greece. We have 3 experimentation facility sites, 1 in Portugal, in Aveiro, and 2 in Germany, Munich and Berlin, and 1 moving experimentation facility site that provides satellite capabilities. This figure shows the blueprint of the 5G VINI facility architecture. The system architecture, as we can see, integrates multiple facility sites, each including the following components: a service orchestration layer and module that take care of the lifecycle management of network slices at the application layer, that is the network slice semantics, an NFVO, which deploys and operates network slices at the resource layer, and we have the infrastructure resources, including access, transport, and core network functions. Some of these functions are physical, while some of them are executed on cloud environment as BNFs and CNFs. And all the components defined in this, in one 5G VINI facility site are from the same or different vendors, and all managed by a single operator. Despite this per site description, the whole 5G VINI facility shall be viewed as a single platform from the vertical side. This brings the need to implement adaptation layers which unify the behavior and features offered in the different sites, abstracted underlying implementation details on individual site, and in this context, 5G provides Vertical with a single entry point to the facility by means of this portal. Now we go from this generic architecture blueprint to a specific realization at individual facility sites. Some 5G facility sites rely on vendor-specific orchestration solutions, such as Norway and UK facility sites, while there are others who make use of open source solutions, as is the case of Spain and Greece facility sites. And for this PoC, we have selected Spain and Greece facility sites based in Madrid and Patras respectively, which are the 5G facility sites which makes use of OSM. As captured in this figure, both facility sites present the same telco stack. We have OpenSlice acting as service orchestration, OSM as NFVO, and OpenStack providing Ving functionality. And to allow for multi-site network slicing, it's important that PoC stacks communicate between them. And in this PoC, this communication occurs at the service orchestration layer using the TM Forum Open APIs. On the one hand, as I said, we have OSM. And having a ZSM PoC, one may wonder why OSM is to be used in this PoC. The reason is precisely the alignment between the OSM stack and the ZSM architecture. In fact, we can see here that the OSM can be mapped to a ZSM management domain, and that the design of OSM modules is compliant with the ZSM architecture principles like service-based management architecture, modularity, scalability, zero touch, and so on. And proof of this alignment is captured in this figure, which illustrate how OSM models provide ZSM services as defined in ZSM 002. For example, to name a few, we have the LCM, VCA placement modules that provide the ZSM domain orchestration services, TSDB, Common Database Object Storage and Auth modules providing domain data services, and the Kafka bus together with OSM-MR providing the ZSM-defined integration fabric, as we can see here. On the other hand, we have OpenSlice. OpenSlice is an open source OSS solution providing service orchestration functionality. And following up TM Forum SIG framework, OpenSlice provides a mediation layer between the network slice consumption, customer-facing services specification, and network slice realization that is about resource-facing services specification. From a CFSS viewpoint, OpenSlice defined a user-friendly web portal for the interaction with vertical customer, capturing their service orders and keeping them informed about the status of the different network slices. From a resource-facing viewpoint, OpenSlice sits atop the NFVO, consuming solo 5 capabilities to deploy and operate the virtualized components of the slice, translating their application layer requirements into virtualized resource layer requirements. And these figures illustrate the architectural framework of OpenSlice. Roughly, the solution follows a microservice architecture, including a set of loosely coupled modules exchanging messages via an active MQ service bus. And for more information of the different OpenSlice models and the architecture, please go to this link. That is the official web page of OpenSlice. The next point of the presentation is to talk precisely about the details of what this PoC is about. The PoC objective is to demonstrate the ability to automatically scale out a slice that is deployed across multiple sites. And the instance is deployed across 2 5G facility sites, namely Madrid and Patras, each hosting a portion of the entire network slice. And for this PoC, we assume that the need to scale is first detected in Madrid and propagated also to Patras to keep consistencies when scaling resource across the entire slice. So according to the PoC objective, it is clear that we need a use case that justifies 3 things. The first one, having a multi-site network slice instance. Second, the need to trigger a scaling out operation at Madrid facility site. And the third one, the need to propagate this scaling operation also to Patras facility site. And the selected use case is based on vertical industry-related NetSAP hackathon involving developers of Spain and Greece. And for this short-lived event, a network slice instance is deployed. And the logic of the use case is illustrated in this figure and is as follows. So first, there is a NetApp submission service where developers continuously upload their solutions, and the NetApp submission portal and the backend service broker are hosted in Madrid. Due to the European Union defined GDPR policy, NetApp's binaries and data must be hosted in the home country. Therefore, the services for managing the NetApp catalog repositories need to be located at both Madrid and Patra's facility sites. During the hackathon days, there is a sudden high demand of portal interaction due to an unexpected prize to winner developers. And the demand is first detected here in Madrid. Thus, the backend hosts of NetApp catalog repository will be automatically scaled here, and the scaling out operation triggered in Madrid is also propagated to Patra's facility site, since this sudden high demand of portal interaction is also expected at Greece site. Unlike Madrid, where the scaling out was a reactive corrective action, the scaling out operation triggered at Patra's facility site is a proactive corrective action due basically to forecasting reasons, to avoid the congestion that we originally had at Madrid. The NetApp hackathon event mentioned in the previous slide requires the deploying a network slice across Madrid and Patras. And the internal composition of this slice and the geographical distribution of their functional components is illustrated in this figure. As seen, the slice consists of three slice subnets, each model as a separate network service descriptor. The network slice subnet A deployed in Madrid according to this network service descriptor, which is composed of 4 BNFs, including 2 load balancers, 1 web server, and 1 backend AP brokering service. Then we have the network slice subnet B, also deployed in Madrid according to this network service descriptor, which consists of 3 BNFs, including 1 load balancer, 1 repository catalog, and 1 catalog database. And finally, we have the network slice C, subnet C, which is similar to NSSB, but deployed in Patras. On this table, we can hide more details of individual BNFs. And please see that the communication at the data plane between Madrid and Patras is performed with a L3 VPN solution. According to this network slice design, the traffic flows is as follows. So the load balancer 1 acts as an entry point, sending incoming traffic to the web server that serves the web pages to the developers. The web server issues requests to the backend AP brokering service using load balancer 2 for scalability reasons. Upon capturing this request, the backend AP brokering service decides the equivalent repository catalog service to communicate with, either to Madrid or to Patras. If Madrid is selected, then the LB3 handles incoming traffic to the AP endpoint of the repository catalog service. The service is supported by a database, which is deployed in a high availability cluster. On the other hand, if Patras is selected, then it is this LB3 who captures this traffic requests from the backend IP brokering service and do the same process as originally did here in the NSSP. This figure illustrates the impact of the scaling operation over the running network slice. The white boxes represent the slice instance as originally deployed for the NetApp hackathon, while the blue boxes show the state of the slice instance after having been scaled out. And to better understand this transition, let's go to the POC user story. So here we have the user story, which basically includes the following steps. The first one is there is a sudden high demand of portal interaction in Madrid facility site. And to model this, a traffic generator sends quite a high number of HTTP requests to the web server. The HTTP requests represent a traffic load surge with a 3-to-1 ratio, which results in higher IOC processing and CPU usage of NSSA BNFs. So this scenario collapses the backend AP brokering service, which is then enabled to forward traffic to either NSB or NSSE. Madrid OSM detects this collapse as part of day 2 activities by comparing the MON collected metrics against the default-defined policies. And based on this comparison, it triggers a scaling out operation on the NSSI. This operation consists in creating 2 additional web service instances and 3 additional instances of the backend AP brokering service. And the new BNF instances are deployed on the local Vim using OpenStack with day 0 and day 1 configuration completed by OSM. After this, then this is mostly for the new BNF instances, but we also need reconfiguration on the load balancers as part of this scaling out operation on the NSSA. We have to reconfigure load balancer 1 so that the incoming traffic can also be forwarded to the newly instanted web servers, while we also need to reconfigure load balancer 2 so that the web page requests can also be forwarded to the newly instantiated backend AP brokering services. So after all these scaling out operations that entail new BNF instances as reconfiguration of load balancers, then the AP brokering service works again. So the load surge that was originated in this first step makes a backend AP brokering brokering service collapses again. So why this is occur? Because when we have this load, traffic load, although having scale, we have lots of traffic here that is unable to be captured by this repository catalog service. So that means we need to also scale this network slice subnet B. So the increased traffic collapses repository catalog service together with the databases. So again, Madrid OSM detects this load surge as part of day 2 activities and triggers a scaling out operation at this NSSB. So this scaling operation consists in creating 2 additional broken AP brokering service instances and a new catalog database, and also for sure reconfiguring again the load balancer 3 so that the incoming traffic can be forwarded to these new instances. And again, with the new scaling out operation complete, then works again. After being completed the 3 and 5 number 5 steps, then the open source MANO notifies the local OpenSlice, informing them that NSSI-A and NSSB have been successfully scaled out. Based on this notification, the OpenSlice detects the scale change in repository catalog service in Madrid. And since OpenSlice is aware of the use case semantics, it decides that a similar collapse scenario may occur also in Patras. Therefore, it takes the decision that the network slice subnet C needs to be also scaled out in the same way as network slice subnet B did, in order to avoid the same collapse as it was in Madrid. So following this approach, the Madrid OpenSlice propagates the same scale change to Patras OpenSlice using TM4 and Open APIs, and Patras OpenSlice checks the requests and forwards it to the Patras OSM, which executes the NSSC scaling out operation. And after completing this scaling out operation, Patras OSM notifies the local OpenSlice instance of this successful scaling out operation, which in turn set back ACK to Madrid OpenSlice instance in response to the age request. And basically, we have the entire slice instance scaling out completed. Now, entering in the 5 last minutes of this presentation, here are some details of the POC work that has been done in the OSM domain. And this part covers the step 1 to 6 described in the previous slide. So it is all about OSM auto-scaling capabilities at one facility site. That is mostly related to OSM, as I have said. Here is again the network slice subnet A topology with more information on individual DNFs, including their resource requirements and their software images. Here's the link if you want to download them. And in this section, we will focus on the web server BNF. The reason is that this BNF, as we say in the POC user story, it is the first to be collapsed as a result of this traffic load surge, and therefore it is the first one to be scaled out. Based on this web server, then the brokering API brokering services will be also scaled out, and the rest of BNFs on the other network slice subnets will also be scaled, as we did see in the POC user story. So the web server scaling decision is based on the MON collected data. To allow the OSM monitoring module know which specific data needs to be fetched from the web server, as well as the measurement collection frequency, we have defined a simple charm in the BNF descriptor. As shown in the figure, this charm consists of a YAML file specifying the 3 metrics that the OSM monitoring module needs to keep track of. We have the number of users, the web server load computed every 5 minutes, and the web server load percentage computed every minute. This is mostly about collecting the metrics. Once these metrics are available, it is up to the OSM policy module to decide when scaling is needed and how this scaling out operation shall be enforced. And to allow automation in this decision, we have filled in the scaling group descriptor section in the BNF descriptor appropriately. And for the POC, our criterion has been the following one. That is, when the CPU load of a web server instance is about 80%, create a new web server instance. And this operation, as we can see, can be repeated up to a maximum of 3 web server instances, as captured here. So we can have up to 4 web server instances executed at the same time. That is precisely this situation we have here. And finally, to end this presentation, here are some concluding remarks. So first of all, saying that this ZSM POC in the entire pipeline is the result of a combination of all ingredients, including research, as we have done in 5GBNI project. We together with experimentation, also executed in that project, and together with standardization, bringing all the results to a SDO as part of a POC. And in this path, we also leveraging open source solutions, including OSM as well as OpenSlice. The showcasing activities for this POC are planned by early April. The current status is that we have automated scaling at individual facility sites, both at Madrid and Patras. That's basically the steps 1 to 6 on the POC user story. And the next step is to finalize the cross-domain orchestration issues at OpenSlice. That is most related to steps 7 to 11 in the POC user story. Here's the wiki page for the POC number 2, the ETSI ZSM POC, in case you want to have a look at it. And that's basically what I want to share with you. I also, at the end of this presentation, I've also included a couple of annexes to provide you with some more details, showing some snapshots about what occurs at OSM layer, and also how OpenSlice works, in case you also want to have a look at it. Thank you.